In this work, we present a novel approach for shape generation from point cloud data. Point clouds are becoming increasingly popular for modeling shapes, with many applications relying on the recognition, manipulation, and synthesis of point clouds. For example, an autonomous vehicle may need to detect cars in sparse LiDAR point clouds. An augmented reality application may need to scan its environment. Or artists may want to further manipulate scanned objects to create new objects and designs. A generative model for point clouds can create additional training data for recognition, complete scanned objects, or synthesis new ones. We are interested in learning a generative model that maps random noise to shapes represented as point clouds. Point clouds can have an arbitrary number of points, so the model should allow us to sample an arbitrary number of points from the shape. We model shapes as a distribution of points, such that points residing on the surface of the shape have high probability and off-surface points have low probability. A cloud of points from the shape's surface can be thought of as a set of samples from this underlying distribution of points. Prior works have modeled a normalized distribution of points, which is difficult to compute and results in prohibitively slow chaining. Alternative methods, such as scans, can be difficult to chain. Our key insight is that we can bypass these challenges by modeling the gradient of the probability and produce a point cloud by moving points along the gradient field. This gradient indicates the direction in which the density grows the most. To achieve this, we need to produce a gradient field. We use a network to model the gradient of the log density, given a sample location x. The network predicts the gradient of the log probability distribution at the point x. Knowing the gradient direction, we can move points towards high likelihood regions, moving to the shape's surface. Next, we will explain how we learn this gradient field. To set things up, we first know that the true distribution of points is non-zero only on the surface, and zero everywhere else. This makes the distribution discontinuous, and so the ground truth gradient undefined near the surface. Instead of considering the true discontinuous distribution of points, we approximate it by smoothing it with a Gaussian kernel and model the gradient of this smoothed distribution. The amount of smoothing controls the granularity of information which is captured in the distribution. When the amount of smoothing, denoted by sigma, is large, the gradient fields reveal a causal shape, and when it is small, it can capture more fine-scale details. We model this gradient field using a deep neural network, g-theta. A simple objective to chain this network is to minimize the L2 loss between the network prediction and the ground truth gradient of the smoothed log density at multiple sampled locations. For example, at a location denoted by x in this 2D case. However, a key question is, how can we compute the ground truth gradient field from an input point cloud? Inspired by prior work, we compute the ground truth gradient field by perturbing the provided points with Gaussian noise. The true gradient at the perturbed point, denoted as Si tilde, is defined to be in the direction of the original data point xi. Then we can do a simple L2 loss between the predicted gradient and the ground truth gradient at point xi tilde. For more details, please refer to our paper. How do we choose the appropriate noise level? In this slide, we show the process of moving points at different noise levels. Large sigma allows us to supervise more area of the space and produce a compact shape without holes, but the shape misses the fine details. Small sigma unveils the finer details of the shape. However, sampling from such fields leads to a non-uniform point cloud. Inspired by Song and Ehrman, we asked our network to learn to produce gradient fields under multiple noise levels. Our network takes sigma as input and predicts the gradient field at that noise level. Once chaining is complete, we can move randomly sampled points to the shape's surface using the predicted gradient conditioned on different noise levels, starting from a large sigma value and gradually reducing the amount of noise. Apart from a point cloud, the model can also extract an implicit surface. This is because we know that on-surface points have high probability, and when the sigma is small enough, the log density of on-surface point is the local maximum. That means the norm of its gradient should be 0, so we can retrieve the surface with a ray-clustering technique using a zero gradient condition. Putting it all together, our approach is as follows. As previously described, given a point on the surface, we perturb it with Gaussian noise and get x tilde. We compute the ground truth gradient of x tilde, and the network takes x tilde and a noise level sigma as input and predicts its gradient. We use an L2 loss to optimize our network. To cope with multiple shapes, we also use an encoder network, which learns the latent code z from the point cloud of the shape, and the network g theta is additionally conditioned on this latent code z for learning the gradient field. Up to now, we focused on how we can learn the distribution of points. To generate novel shapes, we also need to learn the distribution of shapes. There are multiple ways to model the latent code space. We decided to use a latent GAN. But other methods are also suitable for learning the distribution of shapes. We demonstrate that our technique exceeds state-of-the-art performance in both point cloud auto-encoding and generation, and show that our model is able to extract an implicit surface of the shape. We show some examples of generation results on the airplane, car, and chair categories. Generation results from R-GAN, Chi-GAN, and point flow are illustrated on the left for comparison. Looking at our learned latent space, nearby shapes are similar, while faraway shapes exhibit larger differences, which demonstrates that the model is able to construct a reasonable latent space for shape generation. We also show that our model can work on shapes from complicated topology and shapes from non-watertight meshes. Please check out our code and paper, and feel free to chat with us if you have any questions. Thank you!